Welcome to Technocraft Academy. My name is Timson. I'll be taking you through this data structures and algorithms lecture series in Python. The last time from the time we set out to be taking these data structures and algorithms, if you take a look at the infographic material I presented earlier on, I set out the steps, the sequences at which we are going to be taking our lectures. We are going to be starting with a very introductory part, which is the introduction. Then we move towards recursion, and we progress in that order. So right now, the very first thing to do is to attend to the number one on the list, which is the introduction. So the benefit of the introduction is to acquaint us or to get us used to the terms and terminologies we are going to be facing as we progress in our lecture series. So the first thing is to first of all define what data structures are. Of course, we have to understand the differences between data structures and algorithms, how they are related, and what makes them different from each other. Most times we often confuse them together, which is something that is wrong. Anyways, they are two different things. You understand? So, what are data structures? Data structures are different ways of organizing data on your computer. That can be used effectively. Then what are then an algorithm? Algorithms are set of steps to accomplish a task. Let's say in computer science, algorithms algorithms are set of rules of a computer program to accomplish a task. So if you take a look at what I wrote here, it goes from inputting data down to the program running the calculation in data, and of course it stops when an answer is found. You understand? So these steps are what algorithms what are typically that these are what happens behind the scene. You understand? So what then make a very good algorithm? You think about correctness. You understand? Correctness, that is a set of rules you have laid down um, for your computer program to accomplish a task. Then we take a look at the efficiency. The efficiency here talks about the runtime. You understand? The runtime and the memory usage. An application that is very slow and occupies a very that use up a very large portion of your memory is not a good application. You understand? So this now takes us to the conclusion or to the question of why are data structures and algorithms important? They are important for our data processing. You understand? The efficiency and the how good an application is dependent on the efficiency and the correctness of our data structures and algorithms. You understand? So that is basically for data processing. I told you, give an input, process it, and of course give an output. So now we are now down to types of data structures. How do we know the different types of data structures? We are going to know the different type of data structures by likening it to data types. What are then data types? We have the two major data types. We have the primitive data types, and the non what primitive data types. These are the two major types of data types. So under primitive data types, we have the int, we have the float, we have the char, we have the string, and we have the boolean. You understand? So I won't go into details as to what these are, because I believe we should have known these before coming to data structures and algorithms. So these are the very basic thing that I expect each and every one of you to have known. So now let's now move to non-primitive data types. Now non-primitive data types, there are two types of non-primitive data types. We have the linear and the non-linear. So under the linear, we have something called static and dynamic. You understand? So static and dynamic. So what is the difference between static and dynamics? Before I give the differences, we have under statics we have array. You understand? And under dynamics we have the linked list and the stack and the queue. You understand? So that is dynamic non primitive data types, or dynamic linear non primitive data types. So Let me now tell us the differences between static and dynamic linear non-primitive data types. Now, in linear data structures, the static site file, that is the static site file structure, are fixed at compile time. That is why it is static. An example of it is what? Array. While um, in dynamic linear non-primitive data type, associated memories changes. Example are these: linked list, stack, and of course queue. So these are the reason. Then of course we have uh, non-linear data types. On the non-linear data types are, I think we have let me first of all, non-linear data type. No, non-linear non-linear non-primitive data types. You understand? So under these, I said we have linear. On another linear, we have static and dynamic. So now under the non-linear of it, we have something like, say, tree. We have tree. So let me write it in lowercase. Tree. We have and we have graph. We have graph. So that is that. So now let's now move to um, knowing, understanding the concept of algorithms. So let's now look, what are types of algorithms. Types of algorithms. Let me create a tab, uppercase, types of algorithms. Types of algorithms. We have um, we have we have simple recursive algorithms. Simple recursive algorithms. We have simple recursive algorithm. We have sorry, we have divide and conquer. We have divide and conquer. We have divide and conquer algorithm. We have a dynamic programming algorithm. We have dynamic programming algorithm. We have greedy algorithm. We have greedy algorithm. We have um, we have the brute force. We have the brute force algorithm. Then we have, I think, randomized. Yes, we have randomized algorithms. We have randomized algorithms. So these are the types of algorithms that we have. So I think we these are just the introductory part, like I said. So let's now move to recursion. Let's move to recursion. So since we have now understood the various concepts in data structures, terminologies, and terms in the introductory part of data structures and algorithms, I think it now qualifies us to quickly move to recursion. You understand? Recursion. So, what is a recursion? Let me first of all write it out. Recursion. What is a recursion? Recursion is a way of solving a problem by having a function calling itself. You understand? So, when a function starts to call itself, when you create a function, or when you create a function that recursively call itself, it is termed recursion. So why do we need this recursion? Recursive thinking is important in that it helps you to break down big problems into smaller ones. You know, when you need to um, subdivide it, or when you need to uh, subdivide your problem into what smaller problems, that is when recursions is what needed. So how do we know when to choose recursion? Now, if you can divide a problem into smaller problems, let me write it out. um when to choose recursion, when when to choose recursion when to choose recursion. Now, when to choose recursion, one is, first of all, uh, uh, if you can divide a problem into, let me say, if you can, let me just call it out. If you can divide a problem into smaller problems, one, two. if you can design an algorithm to compute the what the to compute uh the nth index, that is number two. Number three, if you can write the code to lead to the list of the what n time, then if you can implement a method to compute all the nth time, then that is when to use recursion. So let's say let me create a file. Let me create a file and call it recursion.py. Recursion.py. So let me create an executable file. Let me collapse this tree so that let me create a word wrap. Sorry, let me create a word wrap. Yes, so that so let's say for example, you have this recursive method. Let me say def. Let me say recursive method. Let me say you have def recursive method, and let me put an n in it. Let me say def recursive method. I'll put an n in it. So if n is less than one, uh, print. You can say something like say print. Say for example, print. And excuse me. You can say something like say print n is less than one. For example, less than one. You can say something like say print n is less than one. Else you can say something like say you can now say recursive. You can have the recursion call itself recursive method n minus one. You understand? So we can now say print n. Now, sorry, excuse me. Can I say something like uh print n? You understand? So yes, so I don't know why it's underlining this. Hmm? Recursive else recursive method. Yes, it's correct. So this is correct anyways. I don't know why it is underlining it anyways. Or I don't know why IntelliSense is trying to underline it. But this is correct. This is just a correct one. So now you will see that here, uh, you will see that we are having sorry, okay, I think I see where recursive, okay, there's a typo here. Recursive, yes. Yes, that's that. So you will see that when I define the recursive method function, and I'll give a condition that if n is less than 1, let it do this. Else, and I'll say I have a function to call itself. You understand? So this is a typical way of making a function what call itself. Or you can have something like say, or you can say, or you can say something like you can say something like say uh def recursive uh, recursive method. You can say something like say recursive method. You can say something like recursive method that equals 0, if n equals 0, return 1. Else return or return recursive method n minus 1. You understand? So we're typically saying the same thing here, that okay, if n equals 0, you understand, return 1. Else return uh, make the function call itself. So that is just a typical way of representing recursion. Then what then is the difference between recursion and iteration? you know um, we are trying to show a recursive way of solving of implementing an algorithm. You understand? So what is then um, the difference between recursion and iteration? So you will see this method I just gave you is what recursion. Let me let me create another file. Sorry, let me create another file. Let me say power of two, power of 2 qy. So this I want to give the differences between recursion and iteration. That's recursion versus iteration. So the from this recursion.py, this is just a typical way of representing a recursive function. You understand? So for every recursive function, this is just what you need. You understand? This is just what is. So you define the recursive function. You understand? It can be anything. This function name can be anything. You can define your recursive function, create your condition that if n equals 0, returns 1, else let the function call itself. So the most important thing is that the function calls itself. You understand? So now let's now go to the difference between recursion and iteration. Then I will tell us when to use recursion and versus when to use iteration. So let's go there. So what is the difference between recursion and iteration? So for example, we want to use power of two to differentiate between recursion and iteration. So let's say we have here def power of 2. I'm going to create a recursive function of it, and of course create an iterative function of it, so that we can from there I will explain their differences and when to use them and when not to use them. So let's say we have something like say def power of 2. Let's say I create a function and say def power of 2, and I say something like I say n. I give it a parameter of n, and I say if of course if n equals 0, if n equals 0, return 1, else return else. I can say okay, uh, power equals power of 2, power of power of 2 recursively minus 1. Understand? I can now say return on uh, power by 2. You understand? So power of 2. So this is recursive. This is the recursive function of power of 2. You understand? So let's now give an iterative version of this. So from there I will now give, like I said, I will now tell you the differences and when not to use them. So let me so we have here we have, let's say we have def of course power of 2. Let's say we have we say n, of course. We now say something like, of course, let me start my initialization. Let's say I equals 0. Then now say maybe power equals 1. You understand? So I now say something like while I want to use a while loop, y1, no, sorry, y I is less than say 1, no, less than n. Now say okay, power equals power multiply by what? 2. You understand? So of course I have to what? Increment it. Can increment I plus equals 1. You understand? So I now say return power. Now take a look at these two functions. You understand? Sorry, this will break out of the loop. It should break out of the loop. Now take a look at these two functions here. They practically do the same thing. This is the recursive uh algorithm of the recursive version of the algorithm, and of course this is the what iterative version of the algorithms. They practically do the same thing, you understand, but one is more efficient than one, you understand. That is just it. So now this now brings us to the differences between uh uh, algorithm and of course iteration and of course recursion. So like I said, this is the uh, recursive version of the algorithm, and of course this is the what iterative version of the algorithms. So like I said, they practically do the same thing. So let's now take the difference, the points to note here. One, in recursion there's no space, because if I have to tell you the differences, I have to tell you in terms of space efficiency, time efficiency, and how easy to code. You understand? So in terms of space efficiency, recursion has is not space efficient, but iteration is what space efficient. When you're talking about space efficiency, we're talking about the memory, you know, the memory usage in application of an application. So that's what it means by space efficiency. So in recursion is not what space efficient, but iteration is what space efficient. Then if you're talking about time efficiency, now time efficiency has to do with the runtime. You understand how fast an application loads, how fast an application runs. You understand. In terms of recursion, time efficiency is a no. You understand. Recursion is not time efficient, but iteration is also is what time efficient. But if you're now talking about the ease of coding, the simplicity of coding, recursion is simple, but iteration is not as simple as it looks. You understand? So recursion seems simpler to code than what iteration. So there are points to note here. The points to note that in recursion, in iteration, uh, no stack memory is required. So you understand? In case of iteration, another point to know is that in case of recursion, system needs more time for pop and push elements to stack memory, which makes recursion less time efficient. The other thing to consider is that we use recursion in the case we know that a problem can be subdivided into smaller problem. So that is that. So when do we now use and when do we now avoid them? As in, when do we use and avoid recursion? When to use recursion is, remember, when we can easily break down a problem into smaller problem. One, two, when we are fine with extra overhead, that is in terms of time and space complexity that comes with it. So when we are fine with the overhead that comes with it, when you are not considering time and space complexity, that is runtime and memory, when that is not your concern, then you can use recursion. Then when we need a quick solution instead of an efficient one, when what matters to you is a very fast solution rather than efficient one, you can think of what recursion. So she understand. Another reason or another use for it, another reason to make use of it is when you want to traverse a tree, especially in the pre-order tree traverser, then you can think of recursion. Then maybe when you want to use memoization, you understand. Memoization, that is when you are ready to use memoization in recursion. This is memoization. I don't Let me give you the spelling of memoization. Memoization. So when you're trying to use memoization in recursion, then of course you can think of what recursion. So when not to use, when do we avoid using recursion? Now, when to avoid using recursion is when time and space complexity matter. That is, if it matters to us, then don't use recursion. You use what iteration, which is this. You understand? Then, remember, recursion uses more memory. So if we use embedded memory, for example, an application that takes more memory, for example, in your phone, is not an efficient one. So recursion can be slow. So you think of what iteration. So how do we write recursion in three steps? Let's say factorial. Let me use factorial as an example. Let me sorry, command A, clean up this whole process. Let me explain um, how to write recursion in 3 steps. How to write recursion. Write recursion in 3 steps. How to write recursion in 3 steps. So yeah, I want to make use of factorial. Let me say factorial. So let me use factorial as a case study here. Now remember that factorial in your elementary mathematics, it is the product of all positive integers less than or equal to n. So you understand? Let's say the positive integer is um let's say 5. So let's say we have 5. You understand? So the factorial of 5, let's say 5 factorial equals 5 say times 4 times 3 times 2 times 1. You understand? That is what 5 factorial. You can flip it and say something like it's say same thing. You can say 1, you can say 1 times 2 times 3 times 4 times 5, whichever way is correct. So it is the product of all positive integer less than or equal to what? N. N in this case here is what? 5. You understand? You understand? So the formula factorial can be denoted by say let's say n is the number, we don't know it. Let's now say that this is what factorial. So n factorial is how we depict factorial anyways. So uh this was founded by Christian Kram, that is in 1808. Yeah, it's none of my business. So it takes only what? Positive integer. Another thing to note about factorial is that zero factorial is what? Zero factorial. Zero factorial is same thing as what? 1. So consider these two things. You understand? N factorial is what? 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times n minus 1 times n. You understand? So that is n factorial. So is zero factorial is what? Zero factorial is what? 1. You understand? So let's now see the steps in practical. First of all, you must have what? The step 1. The step 1 here must be what? A recursive case. Think of what? The recursive uh, case, which is the very step 1, which talks about what? The flow. That is the flow. That is the pattern. You understand? So here, let's use n here. Let's say n factorial. Remember that I told you that from this example here, I said 5 factorial is what? Um, 1 times 2 times 3 times 4 times 5, which can be flipped and can be say 5 times 4 times 3 times 2 times 1. So in case of n factorial, we can have something like say n n times um, n minus 1, n minus 1 times n minus 2, n minus 2 times say up to say um, up to 2 up to what? 1. You understand? So it decreases from here. You know, if I try to um if I try to do it this way, you understand? If I try to do it this way, I try to do it this way. So this is what it means. 5 factorial is 5 times sorry. Oops. Sorry. Okay, let me just write them out. 5 times 4 times 3 times 2 times 1. You will see that it decreases. You can decide to flip it whichever way, but I just want to make use of it to explain this n factorial here. So you will see that from 5 times 4 times 3 times 2 times 1, it decreases. You understand? So you understand? So that is what is happening here. You have n factorial. Let's assume n is 5. So the first thing you have here is what? N, because we have 5 here. So you have n here times n minus 1. Let's assume 5, n is 5. So it will now be what? 5 minus 1, which now amounts to 4. You understand? Then what we have again is um times n minus 2. Let's assume n is 5. It will now be what? 5 minus 2, which is 3. Like that till it gets to what? 2, and you understand? And 1. So that is how it moves. Let's now take a look at it. We can now see that from this n minus 1, you understand, we can equally have something like this too. Let's say we want to take a look at this n minus 1. Now let's take this n minus 1 out. Let's assume this n minus 1 is another factorial. Let's say we have another factorial, say uh, n minus 1. We want to get the value for n minus 1. So let's say we have n minus 1. N minus 1 is the same thing as, now you will now first of all write the first value, which is n minus 1. If you remember, we wrote the first value here, which is n. You understand? Here you now write the first value, n minus 1, multiply by the decreasing value. You understand? You have to multiply it by the decreasing value. What decreases? What is after n minus 1? You should have what? N minus 2. Do you understand? Like that, like that, like that, like that, like that. You understand? So we now have the decreasing value. This now brings us to saying or concluding that uh n factorial is the same thing as saying uh n multiplied by n minus 1. That is n minus 1 factorial. You understand? Because n factorial is n times n minus 1, n minus 2, n minus 2. So from here down is n factorial. That's why, sorry, excuse me. That's why if we have, you know, like we have here, we have 5 here. You understand? 5 factorial, we have 5 here. Now we can say 4 factorial to be, we can say 4 factorial equals 4 times 3 times 2 times 1. You understand? So invariably, if 4 factorial is this, we can as well now say 5 factorial equals what? 5 times 4 factorial. You understand? Because look at this 4 factorial, it is from here down to here. So we can equally say 5 factorial is what? This 5 times what? 4 factorial. So that is what is happening here. This is what is happening here. If you take a look at this, you will see that n factorial is what? N times n minus 1, n minus, so n minus 1 factorial is same thing as what? N minus 1, n minus 2, n minus 3, up till it gets to what? 1. You understand? So that is that. So we can equally say n factorial is what? N times n minus 1 factorial. Now this now brings us to we have now succeeded in what? Subdividing our problem into smaller problems. So this now becomes what? The flow, the recursive what? Case. This is what we now use as our uh this is what we will now use as our what? As our recursive um algorithm. So this is now, we'll now run recursion on. So that's how uh it is now broke. So the first stage is what? The step one, which is the recursive case, which is the flow. We now arrived at this. So let's now see how it is working in practical. Let's see how it is working in practical. Let's say we have, let me put it under recursion. Let me comment this out. Let me comment all of this out. So that I won't lose track of them. So let's say we want to have def factorial, from the recursive flow. So we want to have def factorial. You understand? So we have n. So we have n. So we can say, let's say, mm, let's say, let's say, let me say print n. Example. Let me say print n, and of course, let me say, mm, mm, no, I don't need to print n. let me comment it out. I'll use that later. So let me just say, let me say return. Let me create a recursive case. Return n. Remember, remember from our note, n times, let me copy it, n times n minus 1 factorial. So we now say return n times, instead of writing n minus 1 factorial, you have to make this, you have to what, call this function here, copy it, paste it. You understand? You understand? So the n minus 1 will not come inside inside, it will now become like a method, like a parameter of the what function. You understand? We write the function, it was n multiplied by what, n minus 1 factorial. So to make it call itself, you have to use what, the function, put it here so that it can what, call itself. So let's now call the function. Let's now um, let's now, let's say we want to create a value here. You understand? Let's now say we want to create a value here. You understand? So let's say, uh, to see the value, because we are returning, to see the value we can say, let me say value. To see the value, because we need to see it in the console, we can say print. Understand? We can say print. Let me just say, no, it doesn't matter. Let me say, um let me just say copy. So we want to print it. Let's say we want to print it, and let's see what happens. Yes, you will see that we it recursively called itself, but here we have an information here. You understand? What did he say? He said recursion error, maximum recursion depth exceeded, which means it will hit a breakpoint because we didn't put what, a stopping criteria. You understand? It will hit what, it called itself, quite honestly. That's not an error. It called itself. But the error here is that after calling itself, it ran to what, maximum recursion depth. You understand? It exceeds what, maximum recursion depth. So how do we now check that? Even it will do that, quite honestly. But let's say we want to set the recursion limit to beyond. Let's say we want to set the recursion limit to say 10,000. Let me say import. I want to set the recursion limit to 10,000. Let me say import 6, and I'll say something like 6 dot set recursion limit, 6 dot set recursion limit to say 10,000. 6 dot set recursion limit to 10,000. If I run it, you understand, it will still what, it will still uh it will still exceed. When it now exceed 10,000, it will run, it will now exceed 10,000, it will now still get us to that error. You understand? See, type error, 6 dot set recursion limit, uh 6 dot set recursion limit takes an argument. Okay, two given, takes one argument and two given. I didn't give two arguments. Okay, sorry, a comma, put a comma. So let me run it again. So maximum recursion depth still exceeded. So it ran 10,000 times. She understand, but still what, got to this exception here that says maximum recursion depth what, exceeded. So that is that. So that will now bring us to the step two. This is just step one. So it's now bring us to what, step two. So what will be the step two? Step two. So what will be the step two? The step two will kind of be a kind of base case. A base case. So what is the base case? Here we are talking about the stopping criterion. The stopping criterion. So this will now bring us to what the stopping criterion. So because we have to create kind of stopping criterion, a condition, stopping criterion as a set of condition for the flow to what to meet before, so that it won't run into what um uh, maximum recursion limit. You understand? So let's say, of course, our base case, we should remember that the first thing in our condition should be that uh 0 factorial, of course, remember it is what it is 1. Then the second thing we should always remember is that 1 factorial is also what 1. You understand? So these two conditions will form the basis for our what stopping criterion, will be our what our base case. So let's now rewrite it. Let's now rewrite our this thing, our code. Let's now say, if let's say if uh n in if n in 0 comma 1, you understand, if n is in 0 comma 1, um return 1, return 1, and else you can say else return this. You understand? We can just comment this out. Don't need this anymore. You understand? So if n is what either 0 or 1, if n is what 0 and 1, return 1. You understand? Else return this. So let's see what it will return. So by putting 3, it should give us what 6. Let's see how this is working in practical. So this has not given us maximum recursion limit. But it didn't tell us that we exceeded what maximum recursion limit. You understand? So we didn't exceed the depth. So this time it worked fine. You understand? In this case. So let's now say we want to put 1 or 0. So let's put 0. Let's put 0. Let's put 0 here. So let's put 0 here. If we run it, it will give us 1. Of course, let's put 1 as well to check if our code is really working. So if we run it again, it gives us what 1, because we have said if n is either 1 or 0, that is if n is in 1 or 0, it should return 1. Else it should return n factorial n minus 1. So that is that. But there's still deficiency in this code, because we have not considered unintended case, that is unintentional case, no constraint at all. What if a user or somebody else or uh your supervisor now puts a kind of say, okay, now put -1 here, you understand, and now put -1 here, that again will break our code. Or decide to put a float, let's say 1.5, and here put another float, say 1.5, that will again break our code. Let's see. You see, it said maximum recursion depth exceeded in what comparison. You understand? Because our code said if n in this return 1, so recursion error. So now, how do we do, or what do we do to not have this error as a result of unintentional case? Now that now takes us to what the third steps. What are the third steps? That is the step 3. What is the step 3? The step 3 now says, okay, that is now talking about the unintentional case. Let me unintentional uh, case, unintentional case, unintentional case, which talks about the constraint. It talks about the constraint. You understand? So, how do we um what do we do not to have the unintentional case from throwing us into an error? Now we need to put, because of this, we need to put a kind of an assert statement. So let's rewrite our code. Let's say, let's go to let's go back to our code. We're gonna put an assert statement just to check the intentional case. So let's say we can say something like assert uh, n greater than equals to 0, and say int of n int of n uh, equals n. Then of course positive integers only, positive integers only. You understand? So what I'm saying here is assert this error, that is, give this error message if n is not greater than or equals to 0. That is, if n is negative, and you understand, n is not an integer. So these two conditions has to be met. It has to be, I didn't put or, because if I put or, if any of those things are occur, it will break our code. So by putting and, it means both must be true. That is, it must be what? Uh, it must be a positive integer, it must not be negative, and of course it must not be what? Float, by typecasting it with what? Int method. So it must not be what? Float. So int of n must be equals to uh n in comparison. So let's now see if this will break our code. So by running it, it should not break our code. So say assertion error positive integers only. So that has given them like, okay, you must put only positive integer. Another thing is, let's put -1. Let's put -1. Let's put -1. So by putting -1, let's say it will also throw that assertion error, positive integers only. So that brings us to the conclusion of how to uh, the steps to take uh, to write recursions. You understand the steps in writing recursion. So the next class will now be on Fibonacci numbers. You understand Fibonacci sequence. So thank you. I mean, this brings us to the conclusion of the class. Thank you for your patience and for watching this, or for taking part in this lecture series. And God bless you.